Okay, let's do this time. This is just an addendum. This is hopefully to help clarify what some people aren't understanding going on here. I did this on my CAD program because it's a little more precise, and Photoshop's nice for some things, but if I just want to draw circles and lines, and I want them to be certain distances and have my measurements be precise, you can't beat CAD. You just can't. And so I whipped it out here real quick in my CAD program. Just because it's simpler, I want to draw a circle and fill it, I can do it here. I'm used to this program a little bit. I just can't animate this, so bear with me. I got the Earth in the middle and the moon, which you can't really see. I'll zoom in on here in a minute, but I wanted to explain this. This is a big circle, is the orbital path of the moon. This is scale. 1 inch in this drawing equals 1,000 miles. So what we're looking at here, get in there and make sure it's in the screen. Can I get one more? I got it. Okay. So what I have here is Earth, radius roughly 3959. I just rounded it up to 4 inches just to make it simple. And then moon over here, radius 1079. I just made it 1.1 inch radius. So it's 2.2 inches across diameter, and the Earth is 8 inches across diameter. And but center point to center point of the circle is 242,000 miles, or 242 inches in the drawing. And that's depicted by this red line goes from the center of the Earth to the center of the moon. Then the moon just going to follow that orbital path. That's got a 1.519 million mile radius, or 1,519 point whatever inches in scale. And so I just wanted to show that. I'll go ahead and turn this off so I can zoom to extent, so it takes it off the screen, of course. Okay, so I'll just leave it there. So anyways, what we got here, this is 0 point, this red line's totality. So just imagine, if you will, that you're standing here where the red line touches the surface of the Earth. That line passes directly through the center of the moon, and if you continued it on off the screen 93 million miles or so more, that line would touch the sun. And so this is the point I'm going to call totality. I know the point of totality moves. I just picked one point of totality and had to take a snapshot because you have to have some kind of reference, and that's what I'm doing. So this is one snapshot of one point of totality, and this is perfect alignment. And so everything that I did in my models was referenced to this point. So the videos are 30 seconds long, so the first 15 seconds are the 6 hours preceding this point, and then the last 15 seconds, the last 450 frames, are the 15 seconds after this point. And so every one of those videos hits this point at the center part of the video at 15 seconds, and then continues on. And so all of the angle changes had to do based around this point of totality, just to show how this works. And so if I'll throw this orbit back up here real quick and show you that in 1 hour, where is it? There we go. In 1 hour, the moon will have moved from this point down here at the bottom of the magenta up to here where it's splitting the line between the magenta and the green. Now the green represents the rotation of the Earth. This is 15 degrees. So from where the moon started out up to the top of the green here is 15 degrees. This is 0.55 degrees. The moon has moved in 1 hour. So you can see there's a significant difference. Now this area between the magenta and the green is still essentially our line of totality. That's the line down which, the center of which, is casting the shadow on the surface of the Earth. And this was my contention from the beginning, that if the Earth rotates out from under this shadow that has to be cast down this line, because the sun is still over here. If you know how this model works, all of this is going around the sun, and it's going very, very fast around the sun. But those big numbers are designed to make you think that something is happening here that is not happening. This model is fixed. You can take and apply a circle over it and figure out exactly how many degrees of change goes on per hour, per minute, per second, per day, per whatever unit of measurement you want to use. You can figure that out. This orbit, has a fixed diameter, or well, it has a fixed diameter, but it has a fixed radius, and that's what I meant. They have the moon out here at 1.519 million miles along the track that it's got to follow, and it's going roughly 2200 miles an hour. What was the moon goes 2159.37 miles an hour according to this model at this distance on this orbital track. But the degrees here, the 0.55 is unchanged. You could move the moon to the halfway point, and this is still 0.55 degrees. And as long as you scale down the moon to that point, say go halfway, and you make the moon half the size that it appears here, then it's going to look the same exact to you on the ground looking up at it. It will have moved the same distance by your perception. It will look the same size by your perception. So none of that changes. So this is just a game of perception. You perceive this to be, 1,000 miles, 100,000 miles, 1,000,000 miles. You can't tell because you can't measure distance by looking at something. So you're depending on what somebody else told you. And so this is what I'm taking apart here. This is what we've been told, and this is what I'm taking apart. This is 1 hour. Now if we go to 2 hours, you can see it changes. Everything's going to double. Let me get it back out here so you can see it all on the screen. So now the green area is 30 degrees, and if you were here at that point of totality, you're now 28.9 degrees further east than you were 2 hours ago by reference of the moon. You're 30 degrees actually, but if you're referencing the moon, if that's what you're looking at, 2 hours later, the moon is to your west, and the shadow is to your west, not to your east. East is over here. This shadow can't curve around the Earth and race in front of you based on this model. We know the Earth rotates this way. We know the moon goes this way. Everything rotates the same direction. There's no retrograde motion in this, three bodies, the Earth and Sun and the moon. Everything goes the same direction. So we're going to go to 3 hours, and you see it's just getting worse and worse and worse. And then 4 hours, then 5 hours, and then 6 hours. And at 6 hours, let me take this off and I'll zoom back out to extents. At 6 hours, you are now 90 degrees from where you were to the east. The moon has traveled 3.3 degrees from that point of reference, the point of totality, along its orbital track here. Its orbital speed is constant. You can set your clocks and calendars by it. 29.32 days, that's how long it takes. So this little wedge here, this line between the magenta and the green, is the line along which the shadow is still being cast. So you can see here, I did some math on this just in the calculator real quick. According to this model, course, there there is some aspect change, but I've added that in to give the moon the best chance of actually getting the shadow to move, creep over here further. And it just, nothing you do can make it. If I subtract the sun, because everything, all of this is moving this way down towards the bottom of the screen here, that's the direction of orbit, then the aspect along this line actually gets worse by 0.0411 degrees per hour. It actually closes up this wedge down here to where, and it would be 0.04, it'd be 0.2 degrees. So this would be 3.1 degrees. This would be marginally smaller. I can get in here really close and see, it'd be, 0.2 degrees somewhere in here maybe, smaller. But this distance from this point to the starting point is 227 miles. That's all it is. So in 6 hours, the shadow from an eclipse, if the Earth was stationary, without rotation, I mean, the shadow would have only moved 227 miles in 6 hours. Of course, that's not, what we see, so that can't explain it either. So there's something else going on here that the heliocentric model can't explain. Oh, and just for fun, pull this back out. Everybody that likes the Pac-Man map, there you go. That's 24 hours. So this does, this is a good explanation for why there's a little bit of time lag between moonrise every day. So 24 hours at the zero starting point here. So 24 hours of rotation all the way back around to where we were. You're 12 point something degrees yet to rotate until you catch the moon. So that's going to be just under another hour before the moon is in the same place it was the day before when you were standing here and saw it. But anyways, hopefully this helps clear up some stuff for the people that weren't quite comprehending exactly what's going on here. And hopefully I made it easier to understand and not harder.